In this example, you have two lenses in combination with each other. You've got a converging lens on the left with a focal length of 2 centimeters and a diverging lens on the right with a focal length of -3 centimeters. The first thing I want to do is mark where all the focal points are. So for the lens on the left, the focal points are 2 centimeters away on either side of the lens. So I'm going to put a dot here and a dot here. And for the lens on the right, the focal point is 3 centimeters away from where the lens is located. So I'm going to put a dot here and a dot here. So now we can start drawing the ray diagram. So it's going to look like we have a parallel ray coming off of the object going toward that first lens. When it hits the lens, it refracts through it and goes right to the focal point. So the refracted ray will look like that. And I'll draw a second ray, which goes through the secondary focal point, the F prime, which is this one down here. And when it hits the lens, it refracts parallel. If you want to draw a third ray, you can do the midpoint one. So that'll just go like this, and it should end up going through the exact same spot as those ones. So it looks like everything worked out. So we can draw the image from that first combination right about here. So now that image becomes the object for the second lens. So we'll draw a new ray diagram for that second lens. So I will draw the P ray first. That's the one that goes parallel until it hits the lens. Once it hits the lens, it goes on a line containing the F, which is the dot right here. Remember, this one is the F. I'll go ahead and label those. For the diverging lens, this is the F, and this is the F prime. Whereas for the converging lens, this was the F, this is the F prime. So it goes parallel initially, and then once it hits the lens, it refracts and it goes along a line containing the F. So that means instead of going toward the F, it's going to go away from the F as it has to refract. So it will look like that. Then I can draw the second one. That's the one that goes toward the F prime. Remember, it goes toward F prime, not the F. So this one, you want to draw the line going from here over to, keep going toward the F prime, but remember, once you hit the lens, it has to refract, and it refracts parallel. So that one looks like this until it hits, and then it goes parallel. And then the third one is the midpoint one, which is pretty simple, just passing straight through. These three rays diverge away from each other after refraction, so we're going to have to trace them backward. So if we trace that middle one backward and then the bottom one backward, you see they all kind of hit around that same point. So the image looks like it shows up about right there. So since we have two arrows drawn that we drew, this one we can label as the initial image, and then this one we can label as the final image. So it looks like roughly we have the final image that showed up at about the 10.5 centimeter mark, and it looks roughly, if you compare this arrow to this arrow, about the same size. So it's kind of hard to tell if it's going to be larger or smaller or the same size. So for that one, we're definitely going to have to do some calculations. And that's what we're going to do in part B. So we want to use some equations to determine the exact location and size of the final image. So we're going to do the 1 over di equals 1 over f minus 1 over do. This is for the first lens. So for the first lens, the f is 2 minus, and the image distance going from here down to there is 3 centimeters. So minus 1 over 3. That's equal to, the common denominator is 6, so it's going to be 3 6 minus 2 6, which is 1 over 6. So take the reciprocal of that, and the di is equal to 6 centimeters. Does that match what we had on the image? That means it was the image right here should have shown up 6 centimeters away from the lens. If the lens is at 3 and this is at 9, it looks like we had it in the exact location where it should be, at 6 centimeters. So we can mark this as the first image, or let's just call it the initial image. And let's go ahead and get the magnification of that image. The magnification is equal to the negative di over do, which is negative 6 over 3. So the magnification is negative 2. That means that first image is inverted, and it should be twice as large as the original object, which if you look at it, looks like it pretty much is. So that's not the location and size of the final image, though, so we want to keep going with the equations. So we'll do the next one. Now we're looking at the second lens. The object distance is equal to, we can see it's 3 centimeters away from the lens. So the object distance for that second lens is 3 centimeters, and the focal length is given as negative 3 centimeters. So we can solve for the image distance. 1 over di equals 1 over f minus 1 over do. That's 1 over negative 3 minus 1 over 3. Negative 1/3 minus 1/3 equals negative 2/3. If you take the reciprocal of that, the di is equal to negative 3/2 centimeters, which is negative 1.5 centimeters. So either of those answers is acceptable. And let's see if that matches what we have on the image. That means the negative means it's virtual, so it appears on the same side as where the object is. If we're treating this as the object now, the image appears on the same side, which it does, and it's about 1.5 centimeters from the lens. So if the lens is at 12, the object should show up at about 10.5 centimeters, so it looks like we had it in the exact right place. So that's the distance of the image. So we can say the final answer for this is that it is located at 10.5 centimeters. Let's also go ahead and get the magnification of that one. So the magnification is negative di over do, which is negative 1.5 over do, which is 3. We have 1.5 over 3, and it becomes positive, so that becomes a positive 0.5, so that's the next magnification. So to get the total magnification, the m total, we can just multiply those two magnifications together. So m1 times m2, which is negative 2 times the positive 0.5, gives you a total magnification of negative 1, which means the negative sign means that the final image is inverted, which it is, and the 1 means it's the same size as the original object, because the first magnification doubled it, and the second magnification halved it, so it went right back to the original size.